Thank you, Wavy, and thanks for the organizers for giving me this opportunity to speak to this forum. I will be mostly focusing on the following picture in this talk. What's going on here is basically we have data and we're learning a system from this data. And we're particularly learning what people call classifiers, right? So I'm building a neural network, a random forest, a Bayesian network classifier, where the role of these boxes is to basically take instances and render decisions on them or label them, right? So again, data learning process, I learned this box, which is effectively a mapping from instances to decisions. And people want to know, what do these boxes do? How do they behave? Why are they making the decisions they're making? Are they robust? Are they not robust? And it's particularly challenging because we're not building these boxes as we used to do a while back based on models / assumptions or from domain knowledge. We are just learning them from data, and they're in a sense somewhat of a black boxes. So this has received a lot of attention, this theme in AI recently, and of course the deployment of AI systems have accelerated that. The approach that I'll be pursuing and talking about today is based on a fundamental insight, which is the following: that even though these boxes are numeric in nature, and even though they're typically learned from data, the input and output are often discrete. And I'll show you some concrete examples as we go on. The instance is discrete, an instantiation of some discrete variables, and the decision is discrete. So what does this mean? This means that this fancy box that can have a lot going inside it, and even though it's learned from data, is nothing but a sophisticated way of specifying a discrete function. And as such, I should be able, in principle, to represent that function completely symbolically. I don't need numbers. And that's what we'll try to do. So I'll try to capture the input-output behavior in a symbolic fashion, and then I'm in the world of logic. And then I can do the meta reasoning and think about the behavior or reason about the behavior of the machine learning system completely symbolically. So let's take a concrete example. This is perhaps one of the simplest machine learning systems you can find around. It's basically what people call a naive Bayes classifier. And what you have here is what we call features. You have 3 of them, 3 types of tests. This is what's known as the class variable. And typically, I want to give you test results, and I'm trying to predict, is the patient pregnant or not? And you have these numbers. This is like a prior on the class variable. These numbers here represent the false positive and false negative rates of these features. These gets learned from data. And then what happens is, after you learn this classifier, to use it, you have to do probabilistic reasoning. So you come and tell me someone tested positive, negative. What we do is we assert that as evidence, compute a posterior on pregnancy, and then typically check against the threshold. If that probability crosses a threshold, I declare the person is pregnant, otherwise not. So it's a box that is learned, and then probabilistic reasoning is used to render a decision. But if you look at this box, it is a specification of a discrete function. In this case, the features are discrete, the decision is discrete, and therefore I should be able to get rid of all of the numbers. And in fact, in this particular case, one way of representing the decision function of this machine learning box is using the familiar decision diagrams or decision graphs. And here you see one. This gets used in the obvious way. You give me an instance, let's say someone tested positive, negative, negative. Then you start at the top and just follow the edges in the obvious way. And in this case, I'm reaching the decision that this is not pregnant. Now, interestingly enough, this picture has no numbers, yet guarantee the decisions made by this symbolic representations are precisely the decisions made by this guy. There's an exact match on every instance. And this is not accidental. This diagram was, in this case, compiled from this guy by an algorithm that guarantees that exact match. So now that I have this, I don't need that box. I can do my reasoning, whether it is explanations, whether it's robustness, whether it's proving other properties completely in the world of logic by operating on this guy. Now, when you look at this picture, you'd see that this game actually has 3 dimensions, 3 interesting dimensions. And they can be laid out in the questions I'm going to show you next. But let me just say a word that this guy in particular is known as an ordered binary decision diagram. It's not just an arbitrary decision diagram. We'll talk about this in just a little bit. But the three questions are the following. First, what ML systems can we actually compile into these symbolic representations? Okay, I give you a concrete example here. Can we do it for more sophisticated kind of systems? And the second question is, what symbolic representation are you compiling into? All right, so this was just an example. And that question is important because of the third question. The third question is, what can you do with a symbolic representation? What kind of reasoning about behavior can you do? So we'll talk about this last one, and we'll see that there are a variety of questions that arise. Some are traditional and some are being investigated now because of the new context. So there is a formalization aspect of this game of how to answer or formulate certain questions. But then beyond the formulation question, there is the computation question. So I'll tell you, okay, to do explanations, that's the right way of doing it. Then I have to compute. So the kind of symbolic representation that you compile into end up being very relevant. And this is what I'm going to spend a few slides next on to tell you what that world is, because that's a very rich subject of what do I map into. The OBDD is just one example, but there is a bigger picture there that we need to paint. So let me go ahead and say a few words on the first two questions and then spend more time on the last one. Now, this representation, which people like, the decision diagram or the decision graph, they like it typically because it's intuitive, because when you look at it, you can interpret it. Okay, I'll check whether A is true, I go this way. If B is false, I go that way, and eventually if I get a 0 or 1, then I'm done. This is a particular representation of Boolean formulas or Boolean functions. It's very famous. As a representation, we're going to be looking at it as an example of what we're going to call a circuit. And most of what we're going to be compiling into, in fact, the framework I'm going to be describing is always going to be compiling into circuits. Now, what's the relation? Look at what we call a decision node in one of these guys. It looks like this. You have a variable, Boolean variable. If it's true, you go this way, false, you go that way. We're going to look at this as a little Boolean circuit fragment that looks like this. Look what's going on here. OR gate to AND gates. So this is X and alpha, or not X and beta. Now, if you take each one of these guys and replace it by one of these fragments, you're going to get a circuit that computes the same function as this guy. Let's take a look at a concrete example. This is a decision diagram. And if we do the substitutions that I've mentioned, you get this circuit. So for us, really, this is just a circuit. Now, what makes the OBDD special is that when you look at it from a circuit point of view, it ends up satisfying a whole bunch of properties that makes it tractable. And this is something we're going to spend a few slides on, the notion of tractable. Because I don't want just any circuit representation or any symbolic representation. I'm going to seek to compile the input-output behavior into what we call a tractable circuit. Now, what does that mean? That means if you have a circuit or this or a Boolean formula, they all represent a Boolean function. And there are questions on Boolean functions that are known to be hard. And those questions will be used to do the analysis that I'm going to be doing later when reasoning about behavior. So I want to be able to compute and answer these questions efficiently. Tractable means that this circuit satisfies certain properties that makes some of these questions easy to compute. And you're going to see there is a whole spectrum of questions and spectrum of properties. OBDDs, when you map them into these circuits, they end up satisfying a whole bunch of questions. They end up making many queries tractable, and that's why they're interesting. We're mostly working with what we call negation normal form circuits. They look like this. You have an input and a layer of potentially OR gates that are applied to the inputs, and then ANDs and ORs. So the idea of NNF circuits is you can only have negations next to inputs. But after that, just layers of ANDs and ORs. And then what happens is the following. You have this notion of an NNF circuit, and then you start applying properties to it. And if the circuit is decomposable, then certain queries that are hard become easy. Then you add another property called determinism, then even more queries become easy. This is area known as the knowledge compilation area or tractable circuits area, studies this systematically. people have listed a whole bunch of questions or queries or ingredients that you will need to do, like computing whether a circuit is consistent, whether it's valid, whether one circuit is equivalent to another, represent the same Boolean function, counting the satisfying assignments of a circuit. Basically, these questions are hard. They have certain complexity, typically NP hard or more. And studied how imposing properties on these circuits make these queries easy. Easy meaning polynomial. But they've also been studying what happens to the sizes of these circuits, because what happens is as you impose more and more properties, you get more computational power. More of these queries become polynomial, but then the sizes of these circuits grow. So I'm going to give you an example of two of these properties just to see how simple and intuitive this is, and how sharp these developments have become and influential. So let's do that. And let me just mention also that once you start adding properties of these circuits start getting names. We're going to start with one of the simplest called d-DNNF, which you add just one property to this called decomposability. You get what we call d-DNNF circuits, or decomposable negation normal form circuits. And as you add more properties, you get all the way to OBDDs, which is one of the most tractable representations. So let's take a look at this, okay? This is a Boolean circuit. It's an NNF, so you have only ANDs and OR gates, except for inverters next to the input. And the property of decomposability is pretty simple. It applies to AND gates. And it says if you look at the sub-circuits that feed into an AND gate, and you look at the variables, here LK, here's PA, they do not share variables, all right? So those variables are disjoint. And you need this for every AND gate. So if every AND gate, if you look at the sub-circuits feeding it into it, their variables are disjoint, we will say that the circuit is decomposable, and we call it a d-DNNF. And guess what? Deciding the satisfiability of a circuit that is decomposable can be done in linear time. Satisfiability is, as we know, is NP complete, and so you unlock this class using only this particular property, all right? And if you remember, satisfiability is, I want to know, is there a circuit input that will generate a 1 here, right? It's a difficult problem. Now, let me show you another example of a property which allows us to do things that enable probabilistic reasoning. And this is known as determinism. And if you put determinism and decomposability, you get a new type of circuits that we call deterministic decomposable negation over form. Before I show you this property, let me tell you what it allows you to do. Now we can solve something called sharp SAT. So now not only can I tell you, is there an input to the circuit that generates a 1? I want to count how many inputs. So in this circuit, there's 4 variables. There's 16 possible inputs. I want to know how many of these 16 satisfy the Boolean circuit or generate a 1. If you can do counting, then you can start doing probabilistic reasoning. Towards the end, we'll make this very sharp. So this is like a big deal as far as tractability. And determinism ends up being something very simple, which is for OR gates, if you view these inputs as alpha, beta, and gamma, if you pick any 2 inputs, they have to be mutually exclusive. What does that mean? That means these 3 wires, they can never be no more than one input can be high at any time. So regardless of what input do you apply to the circuit, in this case, we're making all variables high. If you look at any OR gate, at most 1 wire will be high. One of the inputs will be high. In this case, you can see exactly 1. In this case, none of them are high. You will never have 2 inputs to an OR gate that are high simultaneously. And that's determinism. As I said, if you have determinism and decomposability, then you can count the models of this. Okay, so again, the more properties you add, the more tractability, the more reasoning you can do, and the more analysis you can do, as we will show later. Let me just also mention one more thing. Okay, this area of tractable circuits and having these properties, the beauty of it is not just the simplicity of the properties as you've seen, but the simplicity of the algorithms that apply to these circuits. For example, suppose I want to count the models of this circuit, that is, find how many satisfying assignment it has. Now that it is both deterministic, decomposable, I need something called smoothness that I'm skipping. It ends up being a simple pass through the circuit. You start at the inputs, you assign zeros and ones in a particular way, and you move up, multiplying at AND gates and adding at OR gates. And this number 9 at the very top tells you that 9 out of the 16 circuit inputs satisfy the circuit. In fact, most of the algorithms on these circuits are just forward pass algorithms. They're like neural networks. You just walk through them and you do these very complex computations. Counting models or counting satisfying assignments is one of them. So if you do compile your input-output behavior into one of these tractable circuits, in a sense, you're in heaven, right? And again, depending on what you want to do in terms of analysis, you would seek a particular circuit, because as we mentioned, there is a spectrum of these circuits, and each one of them allows certain things to be done in polynomial time. This area is studied under the label, as I said, of knowledge compilation or tractable circuits. There's the notion of a knowledge compilation map, which has been developed over the last couple of decades, starting with this comprehensive paper with Pierre Marquis that laid the foundations of this area, where people would study the various circuit types, their succinctness, their computational power. You can see this diagram where you start with the NNF circuits and you add the composability, you get this. You add more properties. There's a lot of these circuits, as you see. And the idea is, as you go down, two things happen: more computational power, and the circuits get bigger or less succinct. I'll give you a few pointers actually, if you want to read more about these circuits. But a recent survey paper that appeared in PODS, it goes with the tutorial I gave there. This is the database theory conference. This is just from last summer, is pretty current on what's going on there. I recently posted an online course, graduate course, which discusses these in detail. You can see some of the lectures. There's 35 lectures in this course. And you can see dedicated lectures to each one of these circuit types for those people who might be interested in learning more about these guys. But I guess you get the idea that we're going to be seeking to compile into tractable circuits. There is not a single choice. There is a spectrum. Which one depends on what you want to do as far as analysis and so on. And this is the paper I mentioned, the POTS paper. Okay, and just to wrap up this part, let me mention that this area of knowledge compilation and tractable circuits has actually broad reach. Databases, communication complexity, uniform sampling, it's been broadly used and investigated. And you'll see towards the very end, hopefully we'll have time, I'll tell you about the role in computation more broadly in CS. It's pretty interesting. But now let me say a few words on compiling, what kind of systems we can compile. Okay, this will be brief because that's a completely different subject. And then we'll go to talk about the analysis. Long time, you can see the gap here. There's 2003 and then suddenly 2018. So this one from about 2 decades is the algorithm I mentioned about compiling naive-based classifiers into OBDDs, all right? This was about 2 decades ago. Nobody paid attention then. Now it's different. Now everybody wants to reason about the behavior of machine learning systems. So you can see quite a bit of activities recently. We generalize this to arbitrary Bayesian networks. So we can compile arbitrary Bayesian networks into symbolic representation tractable circuits. Recently started compiling some restricted types of neural networks and decision trees and random forests. Now, I'm just going to say a couple of brief things here and 2 more quick slides. But here's what happens. It turns out, believe it or not, that from a conceptual point of view, the simplest compilation is for decision trees and random forests. And the reason is those guys are almost symbolic. In fact, let me show it to you on the next slide. If you look at a decision tree, and a random forest is similar. Look what happens. You have numbers. So this says if x is greater than 2, greater than or equal, go this way, right? If otherwise, okay. So if it's less than or equal, -7. Now, those numbers have been learned by your algorithm. But if you look at this test, x is greater than or equal to 2, that's a Boolean test. So in fact, even though you have numbers, they have been categorized by your learning algorithm. So you can think in this case of a variable X that has three discrete values, depending on what interval it belongs to. And the variable Y, I only need to know whether it's Y1 or Y2, depending on the interval. And here's your discrete function. So this actually does represent a discrete function, even though it has numbers. Now, remember, these numbers, you don't have to do the work. The learning algorithms chooses these cutoffs for you. So as far as compiling into symbolic representation, decision trees are the most friendly creature. They're already symbolic, really. It's just a matter of getting a tractable circuit. Now, neural networks come next in terms of simplicity. The most complex are these, and you'll see why. Because in neural networks, there is no reasoning. Just like in decision trees, it's a forward process. So going from input to output, you just walk through a circuit and evaluate it. So if you're able to really compile the neurons, you're in good shape. Now, when you go to Bayesian networks, it's a completely different story. Why? Because I'm compiling a model. When I give you a model, and how do you go from that model to the reasoning that will be used for classification? That's a very complex process compared to the others. And you'll find, if you look at the papers, for example, that we had on this subject, the ones that are most involved mathematically are the ones for Bayesian networks, because I'm reversing a process. I'm trying to, compile a model, not a feed-forward process. Now, I already mentioned the main insight about decision trees, and as you see, it's simple. Let me just mention one more thing as a teaser for Bayesian networks to give you a sense of what happens behind the scene, and then I'll go to the analysis part. This is one observation. Just tells you what kind of analysis you end up doing there if you're trying to compile these guys, which is not the main subject of this talk. But remember this classifier we looked at. There was this prior probability of the pregnancy, and it was 87. And then we compiled it into a symbolic representation. Now, for this particular guy, if you change this prior to this value, or if you increase it to that value, guess what? The decision function does not change. So you have an equivalence interval for this prior. As long as your number is in that interval, this box is specifying the exact same discrete function. And part of an example of the analysis that underlies this algorithm for compilation is to characterize those equivalence intervals and utilize them and so on. But to make these observations, you have to operate in another world, where the probability is and so on. So I'm going to leave it at this. I'm just going to mention that, again, for this course that I pointed you to, there's a couple of lectures on compiling these types, if people are interested. But I'm going to go on and continue with the discussion of analysis. What can we do with these tractable representations once we get them? That's an interesting subject from a computational point of view, but also from a formalization point of view. It's challenging us in a certain ways because it's posing symbolic questions and logical questions, some of which we have not treated before, and now we have to treat based on context. So let me mention one of the simplest things we started with, which is explaining decisions. Now, explanation is a big subject, right? But let's start small. And here we introduce a notion which we initially called the PI explanation in this paper, later referring to it as a sufficient reason for a decision, and you'll see why. And so the idea is pretty simple. You give me a box, one of these boxes, you give me an instance, it renders a decision on it. Remember, an instance is effectively an instantiation of variables, right? Values of features. So you say, what is the PI explanation? And basically what I do is I find the culprit behind that decision. It's a minimal set of instance characteristics that can trigger the decision. So an instance can have 100 features. We call a characteristic the value of a feature. It's a characteristic. Someone's income is high. That's a characteristic. Income is a feature. Income being high is a characteristic. So you have 100 characteristics, and I made a decision based on this. I find the smallest subset. So I can pick 5 of them, and I say, look, it is these 5 characteristics that trigger the decision. If you fix these 5, you can do whatever you want with the other 95. The decision will not change. All right, so this is one of the simplest things that you can start with. Very useful notion. Let's take a concrete example. In this classifier, Sally tested negative for scanning blood and urine. and it was classified as not pregnant. Say, why did you conclude that Sally was not pregnant? And in this case, we have two sufficient reasons or PI explanations, because the scanning test was negative and one of the blood or urine tests. So if you look at, even though I have three characteristics, these two are sufficient to trigger the decision, and they're minimal. You cannot do it with a subset of the strict subset of that. So if the scanning test was negative, the blood test was negative, I will diagnose as not pregnant. But if the scanning test negative, the urine test negative are also. So I have to have the scanning negative, but only one of these would be sufficient. So these are what we call sufficient reasons. There's only two of them in this case. Another concept, which is very recent from last summer, which I'm going to talk about more later, is the notion of a complete reason. Let me just mention briefly for now. And this is when you take all of your sufficient reasons and disjoin them. So this is where you get this sentence that says, scanning test is negative and one of these. Okay, this is a summary of all of these. It's a disjunction. It's a very important notion, as you'll see later, the notion of the complete reason behind the decision, which is the disjunction of all sufficient reasons. All right. Now, before I go on, let me tell you this theory of explaining decisions based on sufficient reasons and complete reasons is based on a fundamental notion of computer science known as prime implicants. And let's just mention it briefly here because this gives the foundation of what's going on. Boolean function. And this is decades old, right? In computer science more broadly, not just in AI. You have a Boolean function like this over three variables. And the notion of a prime implicant is a minimal setting of the variables that will trigger the function. So in this case, there are three prime implicants. What does that mean? If you set A to true and B to true, this function will trigger, regardless of what the value of C is. And there's no subset of this, strict subset that will guarantee that. Here's another prime implicant. If you set A to true and C to true, you will trigger the function, regardless of what B is and so on. Okay, so the notion of a sufficient reason ends up being pretty simple. You give me a decision. Here's an instance. Someone true, true, false, and this function triggered, right? This is the classifier, triggered, classified as positive. You say why? The sufficient reason ends up being simply, you take the prime implicants and find the subset of them that are compatible with your instance. In this case, there's two of them, A true, B true, and B true, C false. These are our sufficient reasons. So I say, why did you classify this positively? I'll tell you, I have two reasons. Because A was true and B was true, or because B was true and C was false, and both of them are minimal. That's the foundation where this comes from. Now, if you have a negative decision, same story, but you have to work with the complement of the function. So in this case, this was a negative instance. Here's the complement, here's the prime implicants, and then you say to yourself, what are the prime implicants that are compatible with this instance? In this case, there's exactly one. So if I tell you, why did you classify this as negative? I'll tell you the sufficient reason for that decision is that A is false and C is true, right? Now, one of the main issues, if people are familiar with prime implicants, is there could be an exponential number of them. There's been significant work over the decades on computing prime implicants and so on. We're going to get back to this. In fact, this is where the notion of a complete reason comes in just a little bit. But let me just show you another example to see how powerful this can be. This is a classifier. This was a neural network. This examples appeared in one of the papers that I cited earlier. You have here an image at 16 by 16. So you have that many pixels, 256 pixels. Think of these as your Boolean variables. And this is the space of instances, that many instances you have. And the neural network in this case is looking at this black and white image and coming back, we're trying to distinguish zero for as well. Okay, so it's a Boolean function, right? So here's your features, Boolean variables, and this is the classifier, it's a Boolean function. So I can compile this neural network into a Boolean function. And we did in this case. And then what does this notion of sufficient reason give you in this context? Well, I give you this instance and I say, classifier, what do you think? The classifier says, this is a 0. And I say, why did you classify this as a 0? Give me the sufficient reasons. So what are the sufficient reasons in this case? Are a minimal set of pixel settings that guarantee this labeling. And in this particular example, look what happened. 3 pixels. one of the sufficient reasons was these 3 pixels. If you fix these to white, you can do whatever you want with the other pixels, and I'm classifying this as a 0. This is something we learned about this particular neural networks. Pretty powerful, completely based on symbolic analysis, given that we succeeded in compiling it. So what does this tell you? I guarantee you, well, you're going to classify this as a 0, right? I can fool you, because this ensures that these 3 pixels are white. So I know, based on the analysis, that this classifier will classify this guy as a 0. Okay, now you can have, of course, multiple sufficient reasons. Here's another example. This is an image that was classified as a 1. And here's the sufficient reason. It was, if you keep these pixels black and these white, I'm going to classify this as a 1 regardless of what the other pixels are. So that guy will classify this as a 0 because of this. Okay, so this is the now there are some very famous systems out there that does something similar, but in an approximate fashion, not by compiling, by actually sampling, No, this is exact. Whatever I'm giving here is exact. Now, for certain areas, this may not be essential. For others, when you're talking about reasoning about the behavior of machine learning systems, are they going to do this? Are they going to do that? Exactness is important, right? If you're going to hold someone liable, for example. So there is a role for each. But let me get back to this notion of a complete reason behind a decision, because that's pretty exciting. This is a recent advance. So the idea was simple. We know what a sufficient reason is for now. What if you take the disjunction of all sufficient reasons? That's another Boolean formula. We're going to call it the complete reason behind a decision. And the idea is I can get this formula directly without having to enumerate the sufficient reasons and then disjoin them. That's the whole point. Because there's an exponential number of sufficient reasons in general. Now, why would I want to do this? And I'll show you now an example, because there are certain type of analysis you may want to do that in principle require examining all sufficient reasons. And I want to avoid doing that explicitly. So if I capture all of the sufficient reasons using a Boolean formula without having to enumerate them, I can answer these questions by operating on the Boolean formula instead of operating on the individual sufficient reasons. I'm going to give you an example in just a second. But in this connection, there is a notion of a reason circuit. So I don't want just to get the complete reason. I want to get it as a tractable circuit because I want to subject it to further analysis. So that's what we call the reason circuit. Remember, a complete reason is per decision. The reason circuit is per decision. And let's take a look at an example. Why would this be needed? What can you do with it? Very powerful concept. Because in a sense, it summarizes the decision. It gives you one Boolean formula that you can query to find a lot about the decision. So here's an example, another kind of classifier. This is for deciding whether to admit people into college. You've got 5 features. Here they are. And it's in the form of OBDD in this case. But remember, this OBDD could have been compiled from Bayesian network classifiers or random forest or a neural network. Okay. Now, it turns out that we're going to talk about the notion of a protected feature, a feature that we're interested in whether it has been used in making a decision, right? This is relating to bias. Now, we're going to define bias, or we're going to say that a decision is biased if it depended on a protected feature. What does that mean? That means the decision could change by simply changing the values, only the values of protected features, right? So I give you an applicant and you say, admit them. They come from a home, rich hometown. If you will not admit them, if I flip that feature, then it's biased, all right? So we can have more than one protected features, it's clear, right? If you really would change your mind because I've only changed the values of protected feature, you're biased. Now, here's a theorem from this work. I'll show you the citation in just a second. The theorem says, if you accept this decision of bias, a decision is biased if and only if each sufficient reason contains at least one protected feature. So if you compute the sufficient reasons for a decision, and each one of them mentions a protected feature, guaranteed the decision is biased. It will be different. I can find you another instance that only differs by protected features, and you will make a different decision on it. And here's another interesting theorem. Now, we were going to say a classifier is biased if it makes at least one biased decision. So what does this mean? That means even a biased classifier may still make some unbiased decisions, right? Doesn't mean every decision is biased. I just need some decisions to be biased. I'm going to call it a biased classifier. Here's another theorem that says, okay, if you show me a decision and I examine its sufficient reasons and I find that some, not necessarily all, some of its sufficient reasons mentioning protected features, I guarantee you this classifier is biased. So the decision may not be biased because the protected feature does not appear in each one of the sufficient reasons, but if it appears in some, I guarantee you the classifier is biased, meaning even though this decision may not be biased, I guarantee you there's another decision that would be biased, okay? Kind of analysis. Let's take a look at an example. This is Robin. She's an applicant. She got all of these features and she was admitted. And you say, why? And it turns out in this case, there are 5 sufficient reasons, 5 of them, right? If I were to enumerate them, each one of these is a set of characteristics. E true, F true, G true guarantees admission. This combinations, you didn't need all of these 5 features. Now, instead of enumerating these, as I said, I'm gonna grab a function that represents their disjunction, and that's what we call the reason circuit. And this happens to be a reason circuit. This circuit, as a representation of a Boolean formula, is equivalent to the disjunction of these 5 things. And here's the surprise. If your classifier is represented using a circuit of an appropriate type, a tractable circuit, I can get you the reason circuit in linear time. I can extract it from the classifier and the instance in linear time. I'm going to show you the procedure in the next slide. It's pretty simple. So this can be obtained in linear time if your classifier is represented in a particular type of tractable circuits. It works for OBDDs for a type of tractable circuits called d-DNNFs. And recent work, we even relaxed that even more. And it happens to be what we call a monotone circuit. That means very well behaved. It's tractable. You can do all kind of things on it easily, like doing quantifying variables. And the point is, if I were to ask you, was this decision biased or not, you would look at each one of these guys. Okay, the protected features appears in 3 out of 5, not on all of them, so it's not biased. I don't have to do this. I don't have to enumerate these and check them. I can directly operate on the reason circuit and give you that answer. No, it's not biased. And I can do this in linear time on this reason circuit. So you give me a classifier, you give me an instance, and therefore a decision, and you want to reason about it. I go and grab the reason circuit and I tell you what you want to know. Okay, is the decision biased? It's pretty powerful. Just quickly, the computation of this notion of a reason circuit out of classifier turns out to be pretty simple. You do 2 simple things. What we call a consensus operation, which ends up adding some nodes to the circuit, and a filtering operation that removes some of them, and you can get the basically reason circuit from that. As I said, it is more than what I just showed you because it really captures why a decision was made, and you can use it for all kind of things. So just as a teaser here, and this is the paper, it's called On the Reasons Behind Decision. It's pretty recent. There is a section called Computing Queries. What do you do if you get the reason circuit? What else can you do beyond decision bias? And there is a whole list of them, but I just want to point you to one thing, to whet your appetite on this, the counterfactual queries. So we identify in this paper a class of queries which we call even if because. So here's an example. So Susan was admitted by a classifier, and then there's the statement, Susan would still be admitted even if she did not have a GPA because she passed the entrance exam and comes from a rich hometown. It's a subtle statement about the behavior of the classifier. There's very simple semantics for these statements and how to evaluate them if you have the reason circuit of the decision. So this is now like the little oracle. I give you the reason circuit, says, okay, I want to know the following about this decision and about this classifier, and you can start interrogating it, and you can do a lot of these things in linear time. You know, sophisticated, especially when you realize that started with a machine learning box. This analysis is about one of these creatures that people don't know heads to tails from, right? So take it, compile it, and do this kind of fancy analysis. All right, let me mention a couple of words on other analysis you can do beyond explanations. Robustness of decisions and robustness of classifiers. But quickly, we know the notion of a Hamming distance. I presume you have two instances. They're just variable instantiations, and you count how many variables they disagree on, right? So in this case, I have 4 features and 2 settings, and they disagree on 2 variables. We're going to call this the Hamming distance. Now, we're going to use this to define a notion of robustness. So what does this mean? I'm going to talk about, is the decision robust? So you have an instance. This is the instance, and this is the classifier. And what is the robustness? And I'm going to count, I'll measure how many features do you have to flip to change the decision. This is what this is doing, okay? So that's generally difficult on a Boolean function, but if it's represented as a tractable circuit, that could be easy. For example, you can do this in linear time if your classifier is compiled to an OBDD. And you can use this as a measure of robustness. So here's a concrete example. This that I showed you earlier, this was the most robust instance as far as being classified 1, and it has a robustness 3. You have to change at least 3 pixels for the classification to flip. This was the most robust 2. This has robustness of 13. You have to flip at least 13 pixels so that you stop classifying this as a 2. All right. So you can compute the robustness of a particular decision. This is one thing you can do if you got symbolic representation. And yeah, you can talk about classifier robustness in general by averaging over all its decisions, right? So there's that many instances, and for each one of them, you compute its robustness and you average. If you're talking about Boolean functions, the parity function has very little robustness. It's 1. You flip one image and it changes. The OR gate has a high robustness. But just to show you an example here. So what happened here is these were 2. These, by the way, neural network is pretty small, but still illustrative. They're doing these 0 versus 1. Both were compiled. There's 2 of them, and they have relatively similar accuracy, right? And you see the tractable circuits were pretty small. The point is, even though they're very similar in performance as far as prediction accuracy, they vary quite a bit in terms of robustness. So this histogram shows you robustness and how many instances, percentage of instances that attain that robustness. You can see, of course, the blue guy is significantly more robust than that particular guy. Interestingly, typically people don't factor these when learning these things, right? You just training data, testing data, accuracy on the testing data, and we're done. And no, there is actually other dimensions of behavior that matters. And this small example, when someone says, oh, but this is small, so exactly. Let me show you on a very small example how things can go wrong. Understanding the behavior and reasoning about the behavior is very crucial. And we have a handle on this and doing it exactly. This link has a lot of our softwares and some of the papers relating to the subject. You can do other things very quickly. One example of properties that you may want to check is what's known as monotonicity. Just briefly, if you had a classifier, let's say for educational testing, passing or not passing someone, if Susan correct answers include Jack's correct answers, then Susan should pass if Jack is passed. This is pretty intuitive. And you can formalize this by checking whether the Boolean function is monotonic or not. Here's another example. Susan and Jack have the same characteristics, except that Susan has a higher income than Jack. Susan should be approved if Jack is approved. Okay, monotonicity. I'm not going to go over the formal definition, but it turns out that you can check monotonicity easily. For example, if you had an OBDD classifier, this is very difficult, right? I mean, you build a machine learning box. You would want it for certain applications to be monotonic. You have no idea that it's monotonic. Your algorithm cannot guarantee that. It's just doing something else, looking at accuracy and so on. And you learn something that is not monotonic. And these tools, by the way, not only will tell you something monotonic or not, if it's not, it will give you the counterexamples. It will tell you what instances you will fail on and so on. It's pretty powerful. This is the overall picture here, is that we're reasoning about what was learned. In a sense, it is a new role for logic, and at least as far as emphasis. Traditionally, we used it to represent what we know about the world and to reason about the world. And we found out that there is more effective ways in some cases to build these systems by learning them from data instead of modeling categorical knowledge. But what this says, yes, but the box that you just built, that's part of the world, but I'm going to reason about it. So yes, I did not use logic to build it, but I'm going to use logic to reason about what you actually learned. Pretty exciting. And the enabling element here is, of course, to be able to abstract the behavior symbolically. What I discussed is what I would call the compile then reason paradigm, because it is based on making a commitment. I want to compile into tractable circuits. You don't have to, by the way. So there is a whole area known as the verification community of neural networks and so on, plays this game without necessarily compiling into circuits, right? So they use other tools like SAT, SMTs, and so on. The one distinction is if you get tractable circuits, because of this power and spectrum, you have a lot more flexibility in what you can do. If you use a SAT solver, you know, those are limited in what they can do. They cannot count, for example, for you. So you can do certain kind of queries. So it's kind of a trade-off between what kind of analysis, what you want to do versus scalability. I will end here. I will point you to the YouTube channel for my group, which has a lot more material on the subjects that I've mentioned. I will particularly mention again the course, 35 lectures from this fall, which elaborates on a lot of what I talked about. And there is this tutorial, which is an hour and a half from pods. It's an hour and a half, but has a lot more content because I spoke a lot faster than I did today. So by the speed of this tutorial, today's lecture is like 20 minutes. So there's a lot of material packed into this tutorial if people are interested. Again, thank you very much. I think I'm done here. So.